Let's get started, everyone. Welcome back. So today we're going to talk more about streaming and sketching algorithms. We're going to talk about the CountMin sketch. It's going to solve roughly the same kind of type of problem we saw last week on Wednesday, but it's going to have some different advantages and disadvantages. And it's going to kind of give an insight into a broader array of these sketching approaches, so that kind of more common of what most of the sketching methods are like within this world of streaming and in general big data. Before we begin the lecture, I wanted to just review kind of things on the schedule. Okay. There's a lot going on in the class right now. I guess maybe a little bit more jumbled up than I would like. There's a homework which I haven't quite posted yet. I will post at least the PDF of the homework by the end of today. The data sets for it aren't totally ready as of right now, but hopefully will be soon. I'm hoping this homework will be on frequency estimation using streaming. Won't be too hard. So I'm hoping this one isn't too long. I know there's other stuff going on. Okay, but that's one thing. The second thing is the midterm is going to be in class here on Wednesday. For those of you watching online, you have to be in class to take it. So don't forget to come to class next week, Wednesday. So it will be on paper here. You will be able to bring in some scratch paper if you want to work out stuff. I probably don't need it. There won't be I hope not too many calculations. You will be able to bring in one sheet of paper front and back that will have anything you want on it. You can computer generate it. You can write it by hand. I find this is a very good studying mechanism to kind of go through the class and think about what were the key things to put on there. And there might be things you want to put on there that will help you with the exam. I think if you're paying attention and following for every lecture, I think you should be able to take it without any kind of extra kind of note paper that has some cheat sheet or something, but you're welcome to put anything you want on there. And again, a great way to study. And then it doesn't have to be about just memorization. Again, there is a practice test up here. This will be kind of a good indicator of what the actual midterm will be like. I have posted solutions and then corrected solutions for this one online on the discussion threads for Canvas. I recommend looking at the test before looking at the solutions just to go through it. The real midterm will probably be slightly longer, but that hopefully allows me to have more differentiation in the grades, which means that each piece isn't worth quite as much, so that if you miss one little piece, it's like 2 or 3 points off instead of 5 to 10 points off, right? So, and it won't be much longer than that. So if you comfortably finish this within an hour, I think is reasonable to do, then you shouldn't have trouble finishing the midterm we're planning in the 80 minutes you'll have in class. All right. If that one is taking much more than an hour, you probably want to study and like really brush up on stuff. Okay. Any questions on the midterm? No calculators, no computing devices, no thinking machines other than yourself in the so in here for the exam. Try to avoid sitting directly next to each other. People in here, I think, will be pretty close to being able to do that if not able to do that. So sit on the aisles and then try and sit every other seat. Oh, okay. That will be Wednesday. And then your project, you should have been working on the project. I really value the project in this course. When I talk to recruiters, people working as data scientists in the industry, they say the hardest transferable skill, or the skill that is hardest to learn in the university setting, that you often need to learn on the job once you get into kind of so industry, is to work on actual less well-defined projects, how to take all the techniques you've learned and put them together to do something useful and meaningful. If you're doing an undergraduate degree here, you're probably doing a senior project or senior thesis. This is one way of doing it. These class projects is another way, another important way. And so kind of, I think this is, whenever I talk to people from industry, I describe what we do for the class project. They think this is a really kind of great experience for the students. One thing that comes with it, so you're not just doing it blindly, is that you have to get feedback from me, the instructor. A lot of you have come up and talked to me, but I want to meet with every individual group before the end. There are 42 groups. So I'm going to try and meet with all of you this week after break. Okay, so there's a sign up sheet. You can get to it. There's a new version of the project document where we slightly updated it that has a link to a page you can sign up for, one per group. I think there are 44 or 45 slots for 42 groups. So first come, first serve. They're in blocks of about an hour, and we'll optimize them within the hour. If you have constraints within that, you can let us know, and we'll try and do that. They're for mostly, I think, the 18th, 20th, 21st, which is the Tuesday, Thursday, and Friday of that week. Okay, when you come to that, okay, so you're also going to get feedback from your peers. In the Monday of the class, you will need to finish intermediate reports before class and bring 5 copies. We'll try and do it in this room, probably in the hallway as well, where we will pair up or match up the groups into 2 to 3 group sections. You will exchange reports from each other, read through each other's reports, and then give feedback to other people in the group. Okay, and then when you come and meet with me, you will meet with me in my office, and you should come with your group and bring a printout of the intermediate report. I will read the printout of the intermediate report while you're describing it to me, and then I will give you feedback. For those of you who have met with me after class or in office hours, 10 minutes, actually, I can give a lot of feedback in 10 minutes. So we'll try and be so efficient about that. It should be a bit more than your data collection report, right? So not just should be self-contained, should be the description of the project and the goals, what data you're planning to work with, and then what you've done so far, what seems to be working, what's not seems to be working, so I can give you advice on how to kind of wrap up the project, how to set up an evaluation, maybe other techniques to try and apply. Okay, maybe if you 3 people in the group and you want 3 aspects of it and you have 2 figured out, I can give you that sort of advice. Or if you have any questions, this is a good time to bring them to me. All right. That's happening right after a break. It'll be kind of, for me, kind of a pretty crazy week, but it, like also a lot of fun. So any questions on intermediate reports? It's great. So, okay, good. So let's get on with the lecture. Oh, again. Great. So the CountMin sketch, we are talking about, all right, so we're going to talk about these type of linear sketch today. And remember, we're talking about a stream of data. We'll think of this as A1, A2, A3, up to AI, AN. Okay, and each element of the stream will be some element of some sort of domain. Okay, and as we've talked in the class, this domain could mean a lot of different things, but some sort of large discrete domain. Okay, we will talk about what if, a little bit later in the class, if like, what if each element is like a vector instead, right? So high dimensional vector. That'll make sense within dimensionality reduction. There are clustering methods too, although those are kind of they're more complicated than the things we'll talk about in this class. But so right now we're coming from a large domain. The kind of classic examples are IP addresses. You're sitting at a router, or like the K-grams, like so Doge is using to kind of sift through parts of the government. So I'm not going to say anything too specific to the inner tubes about that, but yeah. So they're you can represent these things as these very large domains, and the idea is that that n is too large, so I can't keep track of something for each of the elements in the stream. And also M is too large, so I can't even keep track of, for one of each objects in the discrete distribution, I can't keep track of a single counter for everything, right? But what I can do is I'll say that log n, which is going to be, so I think of this as like a counter. So I can count how many things, log n items, I can count how many things of a certain object I have up to size n. I need log n space to count up to size n, right? And log m, which this would be like a label. Okay, so this would also be okay, right? So if I can describe one of the things in the space, there are m things, I can describe it with log m bits. I can encode the m things in a bit string of length log m, right? And so I can label something in log m space. These logarithms of big things are much smaller than the total size, so this kind of space is okay. Okay, and so the goal is to kind of compute something. So compute kind of statistics on A with small space. Okay, and by small space, I mean it's okay to be logarithmic in n or m, and with one pass over the data. In some cases, if the data is just stored on disk and you're just reading the disk once, then maybe it's okay to actually read the disk twice. But if you're on a router, you only get to see everything once. Okay, so sometimes you can do a lot more with 2 passes than you can with 1 pass over the data. Okay, and there's a bonus question in the next homework about that. Okay, but for now we're talking about 1 pass. Okay, and so what you will be getting out of this will be something S, which we'll call a sketch. It'll be a sketch of the data A, and I'm going to store it in one pass, and with small space, the space of S will be small, and I'll be able to update it as I see new items one by one. Okay. Okay, and so when we are in this setting, remember the domain is a large discrete distribution, okay, which captures models of kind of a fairly broad array of things. Then the common statistics that you want to think about are the frequency statistics, okay, for J and M. Then I want to maintain this f of J, which is going to be, if I look at the set of all elements of A such that A is equal to the value J, and the count of these things. So the cardinality of the set of all the items that match this Jth IP address, a certain kind of k-gram that has to do with something that's the government considers naughty, then we want to try and monitor those things. Okay, so I don't know if Doge seems to be using just k-grams at this point, although they're planning to put stuff into AI models, but those are probably fairly expensive to do anything too complicated with. So their first pass is this sort of k-gram analysis, looking for the frequency or the occurrence of certain items here. Okay. Okay. So, there's a couple of summaries of these things we talked about so far for the Misha-Gries algorithm, which I will review quickly. But that was trying to approximate the frequency for everything. But before I get into that, I want to recall, I want to say there are some summary statistics on top of this as well. So where we think of F1, and these will be useful to kind of understand the algorithms we'll highlight today. So the F1 is uppercase F1 is kind of going to be the sum over J over all of Fj. Okay, and so this is kind of just a kind of funny way of writing just n, the number of things in the stream. Okay, but the reason sometimes they'll write other things. We'll look at F2, which will be sum over Fj of Fj squared, the square root. And so the other interesting one is F0. It's going to be the kind of number of distinct elements in A. Okay. AI spell checking for me live. Okay. Okay, and so this one is interesting. How do I keep track of the number of distinct things in the stream or over some subset? This is a really useful question. We won't talk about this today. There are some really cool algorithms for the F0 approximation, or you want to, how many distinct visitors to a website. I have a bunch of users coming in, or maybe they're visiting websites. Sometimes they sign in with their cookies, sometimes they don't. I want to keep track of the number of distinct visitors on a website. The F2 is notable because it will come up, I'll mention this today, and it's often the case that F2 is much less than F1. If you've taken a database class, this is often referred to as the size of the self-join. Okay, so if you can estimate this, you can predict how big a self-join would be. Okay, but we'll notice that F2 is often much less than F1. This is, if I just sum up the values, that's the F1. This is summing up the squared things, then taking their square root. And if the data set is skewed, so some things have a much bigger count than other things, then only the big things get square rooted at the end, and the small things get kind of washed away. So this is often much smaller. We'll talk about two main algorithms today. And one of them will get a bound that depends on F2, and one depending on F1. The one with F2 is that's a much smaller quantity in practice. Okay. Okay, so before we talk about the new algorithms, let's just refresh on frequency approximation. Okay, and so this is, we'll say this slightly more generally, but we want for all j in this space M, we want to get an estimate fj hat. Okay, and we want in particular so that fj minus fj hat is going to be less or equal to epsilon n. Okay, and we talked about a version of, and so this will be equal to epsilon f1. Okay, so we talked about two versions of this, or we'll talk about a few versions of this bound. For the Misch-Agrees algorithm, we had something slightly better where we had that fj minus epsilon n is always less than fj hat. It's always less than fj. So this is, I'm saying the difference between the two is bounded by epsilon n. With Misch-Agrees, we always knew it was an that our count was an underestimate. It was never an overestimate, so we only had error on one side. Okay. We'll also talk about something today where we get epsilon f2, and this will be the count sketch. Okay, and I'll talk about this at the end of towards the end of today's lecture. We'll first talk about the CountMin sketch, which will be a little simpler, but we'll again get the upper bound where, well, it's going to get the CountMin sketch is going to get something where we're going to say fj is less than, this will be CountMin, fj less than fj hat less than fj plus epsilon n. Okay, so it's going to only have one-sided error again. It's going to be always an overestimate of the true value. Okay, it will never be it's never going to be an underestimate. And this will be the CountMin sketch. It's also going to have with probability 1 minus delta. So it's going to be a randomized algorithm. The Misch-Agrees algorithm is deterministic. Okay, and the CountMin sketch is going to be a randomized algorithm. Okay, it's going to have certain advantages over the Misch-Agrees we'll talk about. Kind of a lot of my research in the space has been, people often come up with randomized algorithms first. They're kind of cleaner and cuter, and there's certain nice kind of linearity properties they have about them. And saying, hey, you can do them often deterministically, and then you don't have to have the extra penalty for dealing with the randomness because there's some probability of failure. So, but we'll talk about kind of this probability of failure mode first. Oh, okay. So I want to. Okay. Is there a question up there? All right. So I want to quickly review the Misch-Agrees sketch. Okay, so I'm going to set k equals to 1 over epsilon, but then I'm going to use k minus 1, so counters, and k minus 1, so labels. Okay, and I'm going to get a bound that's epsilon n by using k this, but we use k minus 1 counters and labels. I could use k counters and labels, and then my bound, I can set k equals to 1 over epsilon minus 1, or, but it's a little bit easier to think of this way. And if you get an off by 1 error on the counters, you'll be doing the slightly wrong thing. You won't get quite the right error bounds. It will work, but slightly off. So I just want to first mention this issue. Then I want to say the data structure of it looks like label 1, label 2, label 3 up to label k minus 1. And I have counter 1, counter 2, counter 3, counter so k minus 1. And then there are basically 3 things I have to worry about doing. So I keep them in this table like this. And there are 3 things I have to worry if I for some AI in the stream. Okay, if AI equals some label j, then what do I do? What? Then I increment the associated counter, right? So if I have a match, right, then I increment the associated counter. Okay. If I don't have a match, then there are 2 options of what I do. Okay. What happens if there's some counter which is equal to 0? So else, if some counter j is equal to 0, then what do I do? Remember? Don't.
You drop it.
So I change the counter j to be equal to the AI, and I set counter j equals to 1. Okay, so they're all initialized at 0. So initially they don't represent anything. That means I have an empty counter. So then I can repurpose this counter or purpose it for counting track of this item I've seen. And then if I don't have any of these where none of the counters are 0, then what's the last thing I do? If not, I have to decrease all counters. So else, then I decrease all of the decrease all the counters. Okay, so a pretty simple algorithm. If it matches a label, you increment it, right? You're keeping track of counters. So if you see something that matches it, you keep track. If you have an empty counter, you can purpose it. And if not, then you have to decrease all counters, and you don't decrease any. You can't do this last operation more than epsilon n times or n over k times. And that means that that the total error only occurs when you do this, and that's bound. And this is kind of optimal. For this error bound, you cannot use less space than what this algorithm uses. Yeah.
What's the thing you said we do if we saw an empty counter?
Then you can set the label to match the current thing you're seeing, and you can set the counter to 1. Okay. So those are the 3 steps you have to remember. Very simple algorithm. You will implement this on your homework. Okay. Today's lecture, we'll be talking about a more general approach. This one, you can think of this as like a data structure, and we're going to think of a sketch data structure. Okay. And so I needed to be able to, for every, remember up here, for all values j, I want to return a approximate counter, fj hat, right? So we're going to think of kind of a data structure for S that has all of the stream inside of it. Okay, so like you have a heap data structure or a binary tree data structure or a hash table data structure, you put all your data into this data structure, and then you have 2 operations. The first one is I update with kind of AI. So I'm inserting a new element into AI. A new element AI into the data structure. Okay, seems pretty reasonable. Today we'll talk about how to delete stuff from the data structures as well. Okay, and the other thing I can do is I can do a query of S of query J, and this will output FJ hat. Okay, so these just think of a data structure with an API that allows me to do 2 things, either insert something in it, this was our insert thing, and a query. And a query thing is if it matches, for Mish agrees, if it matched a label, then I return the associated counter. Okay, if it did not match a label, I return 0. Okay, so that was the Mish agrees kind of data structure implicit in this representation. Okay, we're going to think a little bit more generally and allow for slightly more complicated operations on the update and the query than with Mish agrees, right? I guess the query will be a little bit more complicated. Still not very complicated. But if you think of it more generally, I want both of these to be efficient, and I want the space to be small. With a regular data structure, it must have at least linear space. As the data grows, I must increase the space here. With the sketch data structure, the space is determined by your approximation guarantee, by my value k, and k is less than n. So the total space doesn't grow with the data, but the bigger, more space I allow, the better approximation. Okay. 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 So let's talk about the kind of the key method for today. You will also implement this in the homework. CountMin sketch. Okay. Sketch. Okay. This again, remember, I'm allowed to use these counters and these labels, and I'm going to have one more thing I'm allowed to use that has small space. It's going to be a hash table. Okay, so I'm going to have, this is going to have kind of k kind of these of the counters. Okay, and actually I'm going to have k is going to be equal to 2 over epsilon. So instead of 1 over epsilon or 1 over epsilon minus 1 kind of counters, I have 2 over epsilon, so it's already a little bit bigger. And I'm also going to have t of the hash functions. Okay, and these are going to go from each hash function hj, okay, is going to go from the space of all the elements m into a domain k. Okay, and these hj will be drawn from a family of hash functions, so it's randomized, and the randomness comes from the choice of the hash functions, right? So this is the randomness in the algorithm, and we'll analyze the randomness in the algorithm. This is where the randomness comes from. Once I choose the hash functions, it's deterministic, but it doesn't always work because I might choose bad hash functions accidentally. Okay, and these will be kind of uniform the hash function. So it's not a locality sensitive hash. It's supposed to be the probability of collision between two things. I think I need 4y's independence, but maybe you can get it down to 2y's independence. Anyways, if you pick a standard hash function, it works. Of the ones we talked about earlier in the semester, it works pretty well. Okay, and I lied to you a little bit about the number of counters. It's actually going to be t times k number of counters. Okay, so for each hash function, I'm going to have k of these counters. So we'll think of them in this table. Okay, we're going to have a big table. Okay, and we're going to have counter 1, 1, counter 1, 2, up to up to counter 1k. And for this one will correspond with hash function 1. I'm going to go up to hash function t, we'll have counter 1t, counter, t1, t2, up to counter tk. And then beside here, I'll have counter, this will be j1. And then at some point in the middle here, I have say counter ji. Okay, so, right, so it's this table full of these counters. So I have t rows, and I'm going to have k of these columns. Okay, so I'm not, so what's gonna happen is every time I see an item now, I need to go in and I need to do something more complicated than just finding one counter that has a label matching and update it. I need to use the hash functions in order to kind of handle the labels. Okay. So how's this going to work? So I can basically think on an insert operation, right? AI in the stream. Okay. So then on the insert, I have to do a for j equals 1 to t. So for each of the rows, I need to do something, right? So I need to, I'm going to write this complicated way, and then we'll go and look at this. For the row j, okay, I'm going to look at the hash function of a into that table, and I'm going to do an increment on the counter. Okay, and if you're done C or C++, that's increment operator. That's all right. In Java, that works too, right? Okay, so that's you increment that thing. So I need to do this for t different times, right? So I have an element. So I think of having in here some element of a, and I will apply it a on this hash table that will index into this counter h1 of a. Oh, this will be h sub j. Make sure this is clear. H sub j of ai plus plus. Okay, so for h1, for h2 of a, I will index into a different counter, c2, h2 of a, and I will increment that one. And for this last one of a, this will increment, this will find this counter that it will hash into this counter, and it increments this one. Okay, so every time I see an element, for every row in the table, I think I'll have like 5 to 10, so not too many. For each row in the table, I will need to go and call the hash function. That will tell me which column to index into, which could be different for every different element. Okay, for each row might be different. They might be the same, and it doesn't matter. And then I will find the counter and I will increment the associate counter. Okay. Okay, so instead of just finding the one counter, I'm going to hash things together. So I'm going to keep track of every element. I have these huge number of elements m, right, of possible things. Most I never see. And every time I see something, I'm going to keep track of a counter for it, but it's going to be shared with a bunch of other things. Okay, so my counters are now shared, and they're kind of random how the sharing happens because I'm using this uniform hash table and hash function in order to describe. Okay, so a pretty simple version of a uniform hash table, right? Should be easy enough so far. Okay, I said there are two operations. Now I need to do a query on a value j. Okay, so how do I issue a query now? So now I have an element j. I would like to remember this is supposed to give me fj hat. Okay, so I want to do fj hat. I want to get out my estimate of the frequency, the number of things I've seen for this element j, a particular IP address, a particular kgram that the government thinks is naughty. Okay, so so how do I query this? What do you think? Yep. Good. Great. So I need to somehow look at all the hash functions. So I look at all of them, and which one do I choose? I choose the minimum. Let me write this down first. So my query fj hat is going to be equal to, I'm going to take the min over j in t of the counter in the jth row using hash table j. Oh, I've used j too many times. Let me make this a q instead. For a query where the query is in M, so FQ hat for all. Okay, so I'm gonna look at for each query J, for each of the hash tables, there are T rows. For J equals 1 to T, I'm gonna look at the counter in row J. We use the J hash table, and I'm gonna query it Q, and that's gonna tell me which counter to index. I'm going to look at all of the green boxes for the query, and I'm going to take the minimum of their values. Okay, great. This was called the CountMin sketch, right? And so you can remember it's the minimum because it's the CountMin sketch, right? So that's, okay, great book. Why do we take the minimum? Why not the average or the maximum? Why the minimum?
Well, if H exists in each of the hash function maps many different values to a single value, and for J to exist in all of those rows, it needs to get matched the exact match, because there's going to be more things counted in every counter.
Yeah, great. You got it. So what's happening is for each of the counters, it has counted everything with that query Q. Right? Anytime that query Q came in, it incremented the count. So that counter has kept track of it, right? So it has all the counts there, but it might, and it gets some counts from other things which are hashed onto it. So they're all overestimates. Every counter, we have the property that for all j in T, that counter j hash j of q is going to be greater or equal to the true frequency of q. Okay, each of these is going to be an overestimate. Okay, it's always going to get all of the count. Every time I see something, I go find the same counter. This is deterministic once I pick the hash tables, and I'm going to increment the count. So it's going to have all the counts, but some other stuff will get thrown in there too, right? So they're all overestimates. So if they're all overestimates, that means that if I should turn this, they're all, none of them are going to be too small, so I should pick the smallest one. The smallest one will be the closest to the true answer, right? Because they're all overestimates. So that's why I take them in, and this is the CountMin sketch. Okay, so again, once you have your hash tables and you set up an array of counters, doesn't seem too complicated. Then if something comes in, I have 5 or 10 different hash tables. I think in your homework, you use 5 hash tables, right? I think in practice, I think sometimes they use like 8. And we'll kind of get a sense of why you get those numbers. And so you increment 5 counters, and then you check all the counters on a query, and you take the minimum one because they're all overestimates. Okay, so this is pretty simple algorithm. Implementing this for your homework shouldn't be too hard, right? Okay, let's see a little bit about why this works. Okay. Okay, so start by noting that again, the goal is to show that okay, we're going to show that for CountMin, that f of q hat is always greater or equal than fq, and always less than or equal to FQ plus epsilon n. And we're going to say with probability greater or equal to 1 minus delta. Okay, and I didn't tell you what T needed to be. T is going to be equal to log base 2 of 1 over delta. Delta will be some probability that it does not go as planned. Okay. Okay, so we're going to prove that this statement is true. This will be what we're going to try and show. Okay. Okay, and hopefully it's clear that FQ is less or equal to FQ hat, right? So this follows since we so each counter CJ HJ Q includes count of FQ, right? So it must include the count of the frequency of Q, because every time I saw an item, I incremented those counters, right? Okay, so the interesting part is showing that FQ hat is less than or equal to FQ plus W, and then we need to show that this W is going to be less than or equal to epsilon n, and we're going to show that this is using F1, this bound, which is, remember, is equal to epsilon times the sum over J of Fj. Okay, so it is equal to this. And remember, we're going to set that K, the number of columns, is going to be equal to 2 over epsilon. Okay, and so that 2 is going to show up, or the epsilon is going to be kind of a 1 over K term here, and we'll have to see where that comes from. I have an extra factor 2 I need to carry around, and then we also have these log 1 over delta rows we'll carry. Okay. Okay. So why does this work? I think it's illustrative to kind of see why this works. It's not too hard. Okay, and we're gonna prove this. We're gonna look at some S in M, and we're gonna look at the associated kind of overcount for and some J in T. We're going to look at one row for one item, one IP address. We're going to look at what is the associated value of W, the overcount. Let's try and analyze this. Okay. And so we're going to say that W is going to be a random variable based on the choice of the hash functions. I'm going to call it YS. Okay. And it's going to be so this is the W as a function of, we'll call this WQ. So for our query Q, right? So the W for Q, but this will be the overcount that is determined by some S in this domain. Okay. So it's going to be determined by this S in the domain. This is a different IP address. So it's kind of, what's the effect of it? If it collides, it counts towards an overcount. If it doesn't collide, it's not going to count. All right, so if it collides, then the overcount contributed by this other IP address S, this is the overcount, is the frequency of that IP address, H of S, each equals H of Q. Right, so if there's a collision for this hash table, the J hash table, then I get this as an overcount. Otherwise, the overcount from that other IP address is 0 because it hashed someplace else, right? So probably 1 over K, basically, this is occurring with probability 1 over K, which is the number of columns, right? It's random if they collide. So probably 1 over k, they have a collision. Okay. And so now the total overcount, okay, the total, let's say, actually, this guy would be the value of the overcount as a function of S, right? And the total overcount, W, is going to be equal to the sum over S in the domain M, the sum of these WS's, which is going to be equal to the sum S in M of these random variables, Ws. Okay, so I'm going to call this a random variable X, the total overcount. Okay, and now I want to say, well, this is now a random variable. I can use a concentration inequality to kind of try and bound how much of an overcount can this be. I know that the expected value of X is going to be the expected value of the sum of these WS's, okay? And this is equal to the sum of the, I can pull the sum out of the expected value, okay? And what's the expected value of WS? Of YS? What's the expected value of YS? This random variable. Okay, again, let me look at the random variable here, defined in this way. Okay, it's a value of f of s with probably 1 over k and 0 with the rest of the probability. All right, so what is the expected value of each ys? F of s divided by k, right? The expected value here is f of s divided by k. Okay, because the probability I get in the top case is 1 over k, and 1 minus 1 over k is 0, so I just say that's 0. So this is the expected value of this, but I need it to sum over s. Okay, and actually so it means I can bring out 1 over k, sum over f over s, f of s. This is equal to 1 over k, f1. Right, that's the f1 frequency, which is going to be, and now I can write this as 2 n over epsilon. Okay, so let's say, yeah, okay. Where I've got the 2 on the wrong side here. No, it should be epsilon n over 2. This is epsilon n over 2. Okay, f1 is equal to n, and k should have been epsilon over 2. Or 2 over epsilon. Yeah, I wrote that up here already. K equals 2 over epsilon, so 1 over k is epsilon over 2. Yeah, so so the expected value of the overcount is epsilon n divided by 2. I wanted to bound it as at most epsilon n, so the expected overcount for any one thing is less than that already, so that's good. Okay. Okay, but it might be larger. I want to say with the high probability, with the probability 1 minus delta, so I want a very high probability that that the minimum of all of them is not going to be an overcount. Okay, so I need to say that the minimum of all of them is it's not going to be an overcount. So what's the probability that this one row gives me an overcount of more than epsilon n? Okay, for this I need to use Markov inequality, and that's for a random variable x with I can say where the value of random variable x greater than 0, then the probability that x is greater than alpha is less than the expected value of x divided by alpha. Okay, so if you took foundations of data analysis, you hopefully saw Markov inequality. It's a fairly basic kind of probabilistic inequality, probably the simplest one. Okay, and we're going to do this by setting alpha equals to the expected value of x divided by 2, which is going to be equal to, remember the or no, I want to set it to times 2. Times 2. Okay, so what that's going to be equal to epsilon n. So then this will give me that the probability that my overcount random variable x is greater than epsilon n is less than the expected value x divided by expected value of x equals times 2, which is 1/2. Okay. Okay, so I'm going to get that if I set alpha, and I can, it's true for all values of alpha greater than 0 simultaneously. But if I can set for this value of alpha equals to epsilon n, then I get that the probability is that my overcount is bigger than epsilon n, which is what I cared about, is less than 1/2. Okay, less than 1/2. Okay, so that means half the time each one of the rows does not exceed the error bound that I want. Okay, so if I set k equals to 2 over epsilon, then half the time that row does not exceed my error bound of epsilon n. Okay, this was with one row, but we're going to have t of these rows. Okay, so now we need to look at why we need t hash functions. We have t hash functions, and these are going to be independent of each other. And we're going to set t equals log base 2 of 1 over delta. Okay, and so for one hash function hj that's randomly pulled from this family, then I have that the probability that wj equals x, right, is greater than epsilon n. This was going to be less than 1/2. Right, so that's what the previous slide was telling you. Okay, so if I draw these independently, then I can say, well, what's the probability that they're all going to be that if the CountMin, the min of them, is the best of all of them, and I get t chances to do better than epsilon n. Okay, so the probability that all hash hj has wj greater than epsilon n, okay, that's going to be equal to 1/2 to the power t, because these are going to be independent, because I'm going to have t independent of the hash functions. Okay, so the probability that they all have error greater than epsilon n is 1/2 to the power t, 1/2 to the power t means it goes down exponentially, right? So if I set 1/2 to the power t equals 1/2 to the log base 2 of 1 over delta is going to be equal to 2 to the negative log base 2 of 1 over delta equals 2 to the log base 2 of delta, which is equal to delta, right? Okay, so the probability that all the hash tables exceed that error bound is then going to be bounded by this delta. And so if I make this delta equals to 1 out of 32, then that means I need t equals to 5. Right, so if I get 1 out of 32 chance, I exceed my error bound, and usually if it exceeds it, it's not by too much. But if 1 out of 32, I exceed the error bound, then I need 5 hash functions. Right? If I want delta equals to 1 out of 2 to the power 10, which is 1 out of 1024, then I need t equals to 10. Right, so I can drive the probability of getting a large error down pretty quickly by increasing the number of rows. So usually between 5 and 10 rows works pretty well. I think in the homework ask you use 5 rows. Okay, so it's cool. This is how you combine together individual random things that each has a reasonable probability of doing well, but not great. Only 1/2 the time it does good. But I can combine them together to amplify their effect. This kind of trick of amplifying these things is really powerful. Okay, and this allows me to take simple things that do well, kind of on average, and combine them together to get something that's great. Okay, who's seen kind of this sort of analysis? Is this kind of a new idea, or who's I've seen that before. Okay, how many of you are just in awe and just staring there? Okay, great, awesome. That's what I aim for. I aim for awe, I guess. And I like interaction a little bit if you like questions or comments, but I will be happy if you're sitting there in awe. So, okay. Okay, good. Okay, let's compare. Mish agrees versus CountMin. Okay, so we'll do Mish agrees over here. We'll do CountMin. Okay, we'll start with we'll say space. Okay, Mish agrees if you count the number, we'll count a hash function you can store in roughly the size of a label. It's a bit more than that, but the space bound for Mish agrees is going to be 1 over epsilon of the counters plus labels. For the CountMin sketch, the space will be 2 over epsilon times log base 2, 1 minus delta. Okay? And this is going to be counters plus log 1 minus delta hash functions. Okay, so hash functions are a bit more than a label. Maybe fewer hash functions than labels. So if the log m is super big, maybe this is better. But I have an extra factor 2 and an extra factor log 1 over delta. So think of a factor of log of 5 is some other small constant, or log base 2 of 10. Right. Okay. So an extra factor of like 4 or 5 to 4. So the CountMin is a little bit more space. Okay. This is kind of the deterministic Okay, the Mischigrees is deterministic. It always works. Okay, the CountMin sketch is randomized. So I only get, it only works with probability 1 minus delta. Okay, so it probably, if it fails, it probably doesn't fail too badly. Okay, but it doesn't always work. So I don't have a hard sort of guarantee here. Okay, this one gives an undercount, and this one, and Mischigrees gives an undercount, CountMin sketch gives an overcount. Okay, both of them are biased. They both have bias. Okay, they're not unbiased estimates. Okay, they're both biased. One's an undercount, the other is an overcount. Now, if that mattered a lot, I can add epsilon n to this answer, or subtract it from this answer, or add epsilon n over 2 to this answer, and so I can get it so it's the other one. So this isn't a big deal. Okay, so far, has anything been good about the CountMin sketch? Maybe if m is like super big, so log m is much bigger than log n, maybe. Okay, so the big difference is, I want to say one more thing about the Mischigrees that's also good. The heavy hitters, okay? If I want to get the things which are the really heavy categories, the things that occur a lot, Mischigrees tells me to those. Those are the ones I keep track of. For this one, I must query a bunch of guesses. Or you can pair it with Mischigrees to kind of keep track of the heavy hitters, but you then have to use Mischigrees on top of it. And there are some mechanisms to do, but okay, so this one also gives me the heavy hitters kind of automatic. Okay, so why do people like the count sketch? Okay, let's talk about deletions. Okay, what if you threw a bunch of stuff in your stream? It was huge, right? It was this huge file, or you've been paying attention to a router all day, and then you realize there was a mistake. I want to go back and remove something from my summary. Okay? Mischigrees basically does not allow me to do deletions. Okay, there are actually some newer tricks, actually in the last 2 or 3 years, that said, okay, you can basically keep track of another Mischigrees summary of all the deletions, and if it's not too many, then you can do okay here. But if there's a lot of deletions, kind of a huge number of deletions, like you delete almost everything and a small number of things are left, then it doesn't tell you anything useful. Okay, the CountMin sketch handles deletions in a way which is very clever. Okay, can handle deletions is basically what's called a linear sketch, and any linear sketch can handle deletions. How would you handle a deletion in a CountMin sketch? What would you do if someone said, here's a counter, or here's an element in the stream, but this time subtract the element from the stream, remove it from, yeah? Yeah. You query each of the t-hash functions, and the counter, instead of incrementing stuff, you decrement it. So it's very simple to do. Let's say I have a whole bunch of deletions. I put them in another hash, another table with the same hash functions, and I just subtract those two array of counters. And it just works. The same guarantees hold for the number of things that have not yet been deleted. So I can just check all the counters and delete them, and it's simple as that. Yeah.
So to handle deletions, could you basically do the same thing you did for the insert algorithm with decrements instead of increments?
Yep. So that's right. The same thing as the insert algorithm, but you decrement instead of you increment. Okay, so it's very simple to handle to handle deletions. These linear sketches kind kind of very powerful in that I can kind of keep track of two different sets of data and in different streams from different sources and combine them together at the end, right? Or I can multiply them or add them. I can treat them like I would any object in linear algebra. You typically use matrices for linear algebra, but in an abstract algebraic sense, you can treat them by doing addition and deletion between kind of all you're doing is you're storing this matrix of counters, and you can just subtract matrices of counters or add things and update them using the hash functions. Okay, so it's a very kind of powerful thing, this linear sketch. So this is the main advantage of the CountMin sketch, is that it really seamlessly can handle deletions. Okay, one thing neither of these could do, right? One thing neither could do so far is could handle was bias. There's always an undercount or an overcount, and I can try and do something like, well, I know the amount of bias is at most epsilon n, or maybe I can keep track of the number of decrements I've done in niche agrees, and I can subtract the number of decrements or add the number of decrements over 2. It's not quite an unbiased estimate. It's still going to have bias kind of mixed in there, and so there's another. So niche agrees. Well, it was rediscovered. There's this 1982 algorithm by Misha and Gries, but then it was rediscovered after people in the data streaming, data mining community had discovered CountMin sketch. Before either of these was something called the count sketch. Okay, and this is basically the CountMin sketch, but without the min. Okay, so and this will give an unbiased estimate. Okay, and it will have error bound epsilon times f2, and I argued that f2 is less than f1. Okay, so it's again going to have an array of k columns. Each one is a counter Cij, and it's going to have T hash functions. Okay, H1, H2, Hj up to Ht. Okay, now I'm going to set, so like before, I'm going to have to set k equals to now 4 over epsilon squared. So if epsilon is 1%, this is now 440,000 instead of 400. So this is a bit higher. And t is going to be t log base 2 of 1 over delta. So t now is another factor 2 in it. So it's a little bit, it's a bit bigger. But again, the error bound is going to be epsilon times f2. So the error will be smaller because it's epsilon times this f2 quantity, which is typically much smaller than the total count. Okay. Okay, and I'm going to need 2 types of hash functions also. I'm going to have the hj, which is going to be drawn from here, where hj goes from the domain to k, right? So hj is going to, for some a, is going to index into some counter like before, but I also have a sign hash sj, which is going to be from a different family of these hash functions, and sj will be from the domain into -1 plus 1. Okay, so now I have 2 types of hash functions, and so the update's a little bit more complicated. So now on an insert of AI, okay, so I'm going to say again for j equals 1 to t, I'm going to find the jth row. I look at the hash function j of ai, and I'm just going to get this value. I'll just say plus equals. Instead of always 1, it's going to be the sign of ai. Okay, so sometimes for some things I add 1, for some things I subtract 1. Okay, so I sometimes add, I sometimes subtract. Okay, and what this will give me is that the expected value of any counter cji for any counter is going to be 0. Okay, this is because for any element I add to it, sometimes I'm going to flip a coin basically and have to, depending on the probability from this hash function, the sign hash function, I'm either going to add it or subtract it. So the expected contribution of any object onto a counter is 0 instead of its frequency as before. So now the expected contribution is 0, so I don't have a necessary overcount on all the counters. Sometimes an overcount, sometimes an undercount. Okay? And so this will lead to the stronger bound that I'll have fj minus fj hat is less than or equal to epsilon times f2. Right? So I'm going to get this stronger kind of bound here, where f2 will typically be much smaller than f1. So I have to pay k as much bigger by a factor of 1 over epsilon. But this bound, this actually tends to work better in practice, and it will be unbiased. Okay, I can also say that the expected value of fj hat is going to be equal to fj. So I'm also going to get this unbiased property here. Okay. Okay, one more thing to tell you how this works. Okay, I need how to do a query. Query for Q and M. So how do I do a query? Okay, so I need to set F Q hat. Somehow is going to be a combination of all the counters they hash into, right? So I'm going to look at the counter J. I'm going to hash into the query, and I somehow need to combine all these things I hashed into an estimate. Before I took the minimum of these, how should I combine these now that they're unbiased? Average is a pretty good guess. It turns out the average can be susceptible to outliers. I might get one really big overcount, and that could throw the average off. The median, that's right. So I want to take the median of these guys. Okay? And so the median is why, the reason I use the median is why I have this factor 2 in front of the number of hash tables now. I have to say, what's the probability it's an overcount? That would mean I would need more than log base 2 of 1 over delta things to be an overcount, and the probability it's an undercount. Well, I need log of 1 over delta things to be an undercount, and if I neither more than that by epsilon n or epsilon f2, then I know that all the things close to the median has not too many overcounts or not too many undercounts. And if I have twice as many, I protect myself against both overcounts and undercounts. And the median allows me to get an unbiased estimate here. Okay, so I get an unbiased estimate. It's a little bit bigger, but I get slightly stronger error guarantees. Okay, and this is called the count sketch. Okay, so this is, I won't ask you to implement the count sketch. It's a little bit trickier to use. It actually, of these, probably the most famous. If someone says, how do you do frequency approximation in a stream? They'll probably tell you the CountMin sketch. Okay, and I'm friends with the authors of the CountMin sketch. It's very cool, simple analysis we did in class. But it's biased, it's randomized, so you have to pay for that. So there's more space than Misha agrees. You have to query to get the heavy hitters. But it can handle deletions, but the count sketch can as well. And the count sketch can do it, and it typically works a bit better. Okay. And so I suggest either the Misha agrees with some variants I could tell you about to optimize it, or the count sketch for these two things. But you'll implement Misha agrees and the count sketch for your homework. Okay, and the midterm is next week on Wednesday. Make sure you come in class for the midterm. One sheet of paper both sides, no calculators or anything. And good luck. I'll see you Wednesday. This week. Midterm is this week, Wednesday. So in 2 days from now, right here. Thank you.